In this short video, I'll be walking through the workflow and use of the software, which allows the users to perform image and audio manipulation. A bespoke user interface is developed using tkinter for Python to improve productivity, allow edits, and enable a seamless bidirectional translation between auditory and spatial modalities. We can start by uploading sample music to the audio playlist. Please note the acceptable formats are either WAV or MP3 files. Once uploaded, we can see that music is cut up into a series of 5-second intervals. This is due to the capped resolution of the pix-to-pix algorithm set at 256 by 256 pixels, which converts to roughly 5 seconds of audio. By clicking on the desired sample, we can choose to play it. Or visualize it as a MEL spectrogram. Please note that the frequency range for the spectrogram is inverted, with high frequencies located at the bottom of the image and low frequencies located at the top of the image. Once converted, we can choose to click on the large left pointing arrow to perform an image translation. This process utilizes the pix-to-pix algorithm originally developed by Philip Isola in 2016 and is executed through the high-level TensorFlow API. After training on many thousands of image pairs, the model learns feature translations and can produce architectural sketches from different pieces of audio. By uploading different pieces of music, we get different architectural sketch representations. We can choose to switch between section, plan, or elevation translations, converting music to either section, plan, or elevation drawings. Due to the stochastic nature of neural networks, unfamiliar inputs tend to generate noisy outputs. In such cases, a set of image brushes are provided to draw over imperfections. The brushes themselves can be replaced with any images, though it is recommended to base these off the initial training dataset for consistency. Once translated and edited, the drawings can be saved to the image timeline, where each row correlates with either the architectural or auditory modality. Here, drawings can be interchanged between the workspace or exported as numeric data into Grasshopper, where further scripts translate the raster data into vector line work, creating parametric, drawing-informed architectural elements. These can also be joined to far more complex combinations, such as sections dependent on plan constraints. To an extent, this system also works bidirectionally. The generated architectural drawings can be converted into music. By pressing on the right pointing arrow, a new spectrogram is generated. By further pressing the Audio Generate button, here we can use the Griffin-Lim algorithm to reconstruct audio from a spectrogram. By deactivating the audio playlist, we can play the generated audio. Because the modality of the image is the intermediary between architecture and sound, it is possible to make edits through image adjustments such as brightness, contrast, and sharpness. If we are happy with our work, we can choose to save it either as an image or a piece of audio. On the other hand, if we are unhappy with the output, we can always clear the canvas and start again. It is also possible to draw over the spectrogram with dedicated spectrogram brushes. Finally, on the right side, we can find the audio effects panel, including a variety of audio effects pedals. Here, we can choose to edit the sound wave of the spectrogram and represent it with added effects. The final timeline can be played and saved as a whole composition. With this, we conclude a brief overview of the user interface, which is used as the primary tool for the architectural design of the project.